So we would like to welcome everybody who joined already. We are a group of people who are interested in Rust. We are mostly based in Wrocław, but we are happy that people from all over the Poland and other places joined us today. And we haven't done much online events yet, so we would like to ask you to give us any feedback after the webinar, because probably there are some things that we haven't thought of, and some things that we could improve in the future, because we do plan to host other events of such type in the nearest future. So Bartek, maybe you're going to introduce Rafał and the talk itself.
Okay, so today this is our second edition of our webinar, and Rafał would talk us about smart pointers in Rust, about his journey with them. Rafał is our member since I remember actually, so he I don't know if experienced Rust developer in terms of like professional experience, but he worked with Rust for some time, and I think it's at least second time he gives us talk. So welcome, Rafał, and I give you your time.
Okay, thank you very much, and welcome everybody once again. I hope you are doing well in this strange times, and thank you for joining and your interest in Rust. I hope you can learn something new today. Okay, so we decided to do the questions and comments section at the end of the presentation because of the online meeting. It's sometimes hard to do the interactive discussion, but I would like to ask you to interrupt me immediately if you hear me talking bullshit, so we can immediately mute you or fix the presentation. The difficulty is kind of more novice than intermediate, but being acquainted with the Rust syntax and the memory management topics would definitely help. So C++ developers will not have any trouble understanding what is going on here. So this is my CV. Magister engineer, software developer. I occasionally speak at meetups, doing some contributions to Clippy, Rust Clippy. I created several pet projects in the evenings. I don't have any commercial experience with Rust yet, but that's gonna change soon. Currently, I work at Taumatech, a software house specialized in developing IoT applications, unfortunately not in Rust. I'm gonna work there for actually 2 more days, and then I'm changing jobs. Okay, what are we gonna talk about? Pointers, smart pointers, containers, interior mutability, and we're not gonna talk too much about all this stuff in the multi-threading context. Let me explain you why, because this presentation was originally intended as a lightning talk about smart pointers. Then to cover the RC RefCell combo that we're going to talk about later, I decided to add some info about the containers. But when I tried to put also the multi-threaded ones into the mix, the entire thing just became too convoluted, and I decided that maybe multi-threading in Rust is topic to be covered on a separate talk, maybe by some of you, who knows. So we will scratch the surface of the multi-threading, but we will not deep dive into it. Okay, a pointer. So not everyone is aware of it, but there are row pointers in Rust. So you can use them, not freely. But as you can see in the code here, they are available and easily display the memory location address. You need to be explicit whether your pointer in Rust is const or it should be mutable. So this is unlike other places in Rust when everything is considered not mutable. In case of pointers, you have to be explicit. And I actually used this functionality at least once. I have some strange formula to calculate the size of a vector I'm gonna need. Then to increase sureness, I wanted to check if this vector never relocates, so that I correctly calculated the required size. So I created the vector, I checked the address of the internal buffer, then I put the elements in. At the end, I again check this address. And if both these addresses are the same, the vector didn't relocate. So it's cool and quick. I'm not sure, maybe there's some better way to do it, but this is how I approach the problem. Okay, the row pointers in Rust cannot be safely dereferenced. So if you try to read the value that is stored behind this pointer, you cannot do it, because Rust simply doesn't have any way to assure that the location is correct, that the memory exists, and that the process have access to it. So your code going to be rejected with the dereference of row pointer error. But you can help yourself with unsafe. But better do it only if you know what to do, or if you don't have a choice, because sometimes you, let's say, interface with the libraries written in C, and you have to use these pointers to communicate. There's a lot of unsafe code in the standard library anyway, like Rust is built with these unsafe internals. And I'm actually still wondering how Rust team guarantees that the internal implementation of, let's say, hashmap is absolutely safe. But this is maybe another good topic for a separate discussion. Now, going to the smart pointers. The idea behind smart pointers is basically all about ownership. We need to know who owns a piece of data, because owner has the responsibilities. He needs to release the memory only if it's no longer needed by anyone. It needs to do it safely, and it needs to do it at all. In case of row pointers, you are the owner, and you, as every software developer, can introduce bugs, and you will introduce bugs no matter how smart you think you are. And maybe the last point, I mean the at all, is not fully correct. If I remember correctly, Bartek mentioned possible memory leaks in his recent presentation. Rust uses the RAII to release memory, but Rust can be tricked into leaking a memory. It's not going to cause any compilation errors because memory leak is still considered safe. What kind of smart pointers we have? Box RC, which stands for reference counted or counting. ARC, it's atomic reference counting. Weak, cow, maybe some more, I don't know. I don't know of any. But there are probably several interesting ones in the external crates. If you know some of them, I would also encourage you to tell me about them at the end of the presentation. I know that there is at least one called Super Cow. I didn't have time to investigate it though. So, okay, let's briefly discuss each one of those. One more thing. This is the former form. Like, a long time ago, box in Rust was represented by this tilde sign, and the reference counted pointer was represented by the @ sign, but it was long before I even knew Rust exists. Okay, let's start with a box. Box is the smart pointer that keeps exclusive ownership of the memory. Sometimes you don't, or you can't, or you or doesn't want to keep the value on the stack. Maybe it's too big. I don't know that this too big is not strictly defined. It could be 1 megabyte, it could be 100 megabyte. Or if the size of the object is not known at the compile time, like trait objects, for example, you need to keep them on the heap. I actually quite like the name box. I think it shows very good what the box is intended for. If any one of you played the game Factorio, you know what I mean. There are boxes that always occupy the same amount of space, one tile, but you can put everything inside, like, let's say 100 cars or 50 oil refineries, and the box still remains small. It implements the Deref trait, so it shines in conjunction with the Deref Coercion. For our Polish speakers, this means przymus dereferencyjny. I will get back to this Deref Coercion in the later slides, but this Deref trait means that you can treat the reference to box as the regular reference. So as you can see in the code here, you can dereference regular references, and you can also dereference box and just read the value that is stored inside. And since the box owns the memory, mutations are freely allowed. For all C++ developers, this is kind of like a unique pointer. And again, this is some kind of curiosity. Also, a long time ago, we used to have this kind of syntax to create boxes. Next, we have the reference counted pointer. So this guy lets you share the memory and have multiple owners. Memory stays valid as long as at least one owner exists. We're going to see the examples in the next slides. But what is important from the point of in Rust, that there are mutations are not allowed, because you have no single clear owner. You're never going to know who's going to access the memory, so you are not unable to change it. For C++ developers, it's kind of like shared pointer, with the exception of the mutation. And there is also another difference, because this one is not going to work in the multi-threaded environment. Of course, there is no need to remember that if you try to use RC in multiple threads, Rust will not compile your code. And why it is not safe to send it to another thread? Because internally it counts the active references, strong references to the memory. And this counter is not modified in an atomic way. So this is the difference from the shared pointer from C++. So as you can see here, you can modify box and change the value stored inside, but in case of RC, you're going to get compilation error that you cannot assign the value. Okay, let's take a look at some code. Let's see, we decided to keep the small data on the stack, but the huge one on the heap. Let's imagine that this string is very, very, very long. So we have this a few functions. We create the data. In case we are trying to get the small data, we simply return the value. And in case we're trying to get the huge data, we return the reference counted pointer containing this string. And inside, we just cloning this pointer and making another strong reference. Now, what we have here, I'm not sure if you can see my mouse pointer. I maybe do it like that. Let's say we have some database, and these three guys get the value of the small data, like this I32. Then we print it, and again, these three guys get the huge data. Now we're gonna print all these 6 values. What we can see here, we get 3 ones, 3 times long string. But the difference is that these 3 guys have their own copy of the data, and this only have reference. Here we can also investigate some debug data. For example, if we check the strong count for this reference, we see that there are actually 4 of them. One is here inside the database, and another 3 are here. We can use the ptr eq function to verify, double check if we really have, if we are really pointing to exactly the same location. And if we, for example, at this point drop the database, this RC will get destroyed, but the string will remain intact for these 3 guys to use. But as you can see, the strong reference count will now be 3. Okay. So please note that thanks to the borrow checker and lifetimes in Rust, you can enforce such behavior without the heap by using regular references, because all this data lives in the same scope, at least as long as you don't try to manually drop anything. Rust will allow you to enforce the correctness of these references. And by the way, we can see another nice feature of Rust here, which is the shadowing. Here we are not modifying these 3 previous values, we are just creating new binding. And the old one still exists, it's no longer accessible and will be destroyed here at the end of the scope. Okay, what is going to happen if you try to use RC in the multi-threaded environment? And please excuse me using the most classic example. You can find it everywhere, but it's so simple and straightforward that there's no need to try to come up with something different. Your code will not compile because the RC cannot be sent between threads safely. So here comes the ARC, the atomic reference counted. In case you didn't spot the difference in the code, we just simply replace the RC with ARC. And now for C++ developers, this one resembles the shared pointer more, as the internal reference counter is manipulated atomically. So as you can see in Rust, you must be explicit about your willingness to pay this additional performance cost, because manipulating the counter in atomic way is more expensive than doing it in non-atomic way. The send and sync markers traits mentioned here are marker traits that indicate that whoever was responsible for creating this type T, he took care to make it thread safe. More details, I think, are out of scope now, but this code will compile and will be safe. And well, if there's shared pointer, there must be weak. Actually, there are 2 different flavors of weak pointers. One is for RC, one is for ARC. And these are the results of downgrading RC and ARC, respectively. And they are smart in a way that they can tell if reference is still valid. Creating such pointers does not increase the reference count. But before you use it, you need to explicitly try to upgrade this to the strong pointer. Oops, this is a mistake. So let's see what we have on the left. We are creating the data here inside the internal scope, and also we are creating quick pointer to this data inside the scope. The scope ends, the original data is destroyed, and we try to update the weak pointer, and it will not work. The data is no longer accessible. And on the other side, code is very similar, but this time we create the data outside of the internal scope. So in that case, if we try to upgrade the weak pointer, we're gonna receive the original data. Okay, cow. Let's see what kind of animal is that. The name stands for clone on write. So it provides immutable access to data, but at some point in time when needed, it can provide mutability, but it will take the contained value and make it owned. So like the cow will steal your data, and then this data can no longer be shared, but they can be mutated. So here's a simple example, like you're accessing the text file from the read-only network share. You can read it as many times as you want, but if you wish to make changes to this file, you need to make your own copy. So let's see this in action. Here I have some struct huge data. Actually, I have the trait clone implementation for this huge data, so we can see some output on the screen. Here's the code. We're creating this huge data and created a borrowed cow. A cow comes in two flavors, borrowed and owned. One-way transition from borrowed to owned is possible. And as long as the cow remains borrowed, it acts as a shared immutable reference. Once it becomes owned, it acts more like a box. So here's the output. We're gonna see number 1 here. But if we try to mutate this cow, it's gonna be converted to owned one. Internal value will be cloned. We can see this here. And you are free to mutate this number and do whatever you want. But you cannot make it back to the borrowed state. And this text example shows generally why I think that cow deserves a separate talk. I'm curious if there are more tricks like that possible. Maybe you know about them and we can discuss later. So let's see, this is actually quite common code that you want to describe some error code. These strings are static, so for maximum performance, you decide that you will just return static references to the data that simply sits in the memory in fixed place. Everything is working correctly. But then you decide that for some cases, you would like to provide more details in the error description. Now the code no longer compiles, since format produces the own string, and it is anything but static. So basically, we cannot have static reference to the locally created string. So what you gonna usually do, and what I did hundreds of times in C++, you just change this returning value to some own string. You decide to refactor, but the drawback is that now every message is converted to non-static string, even these that are static. And in case you have similar functions in several places, you still need to refactor all of them. So what you can do instead, you can just use cow. And yes, this code will compile and it will work this way. So for these strings, it will keep reference to the static string inside. But in case you want to return some owned data, the cow will immediately will come to existence in the owned state. Will consume the string and will carry it outside of the function. So I think this is like a very cool feature of this smart pointer. We can see what is going on if we just take a look inside the source code of Rust. If you are creating cow from a reference, you're gonna create a cow which is borrowed, and we'll share the reference with you. But if you create it from string, it's gonna start in its own form, consume the string, and we'll just carry it on, pass on to the caller, to whoever uses it. Now let's back to this Deref coercion I mentioned earlier. Again, for our Polish speakers, this is przymus dereferencyjny. And the definition is that If type U can be the reference to other type T, then reference to U will automatically act as reference to T. On the right side is more strict example. So if box of I32 implements Deref trait for I32, then this reference to box can be used in every place when the reference to I32 is expected. And by the way, this multiple dereferencing will fit as well. And here you can see some text from the Rust documentation that this rule is the only place in which Rust does automatic conversion for you. In all other places, any conversions must be explicit. And this is done for the convenience. And as we can see on the next slide, we have a function that takes the reference to I32 and prints the value. So you can use regular reference, you can use box, you can use this strange construction. And if there is no Deref coercion, you're gonna need to do it manually, and this strange combination of characters will be required. So just for convenience, this mechanism was introduced. So you can just drop box or other smart pointer everywhere where regular reference is expected. Okay, that covers the smart pointers part of the presentation. Here's a short summary. And as you can see, there is no combination to get both shared and mutable pointer. If it's shared, it's not mutable. If it's mutable, it's single, and there's no shared mutable state by default in Rust because it's dangerous. But after all, we have the linked list in Rust and it compiles well, so let's see what we can do about it. Let's briefly talk about the mutability. By design, Rust exhibits the so-called inherited mutability. So whether something is mutable or not is defined at the binding level. It's all or nothing approach. So you cannot do stuff like in C++ that you define particular field as mutable or const. In Rust, binding, which is represented here, defines whether the entire struct will be mutable or not. Interior mutability is kind of trick to change that, to bring the mutable keyword from C++ into Rust. It will allow you to modify the values even if you only have the non-mutable binding to it. Why this is needed? I mentioned some examples here. For example, you would like to implement some kind of caching that you pre-calculate some data and store it in internal buffers before returning it to the user. So the next time user asks for this data, you can quickly have it at hand. It's help with lazy evaluation. Maybe you would like to collect some performance statistics inside your code or collect some debugging stuff, or you're implementing the reference counting pointer and would like to increase, decrease the reference counter. And this mutability is required because we don't want to pollute our API that we present to the external user with, or maybe the other way. We don't want to force the user of our API to use mutable bindings. For example, if you provide your user with a function to calculate factorial, but you also want to internally measure the time it takes for your algorithm to calculate this factorial, you shouldn't force the user to create mutable bindings. You should think that he is using the non-mutable code. What tools we have to achieve this interior mutability? We have the unsafe cell. This is the only core language to to achieve this effect, it's not to be used directly because it's unsafe. So Rust uses this basic tool as a foundation for more sturdy wrappers. In particular, these are cell and RefCell. Cell is simply a mutable memory location, provides this functionality of the mutable keyword, and owns the memory location. RefCell is very similar but works on borrowed data, provides access to mutable references, even if you only have non-mutable reference. Okay, there is also this never sync that I should briefly describe. It basically means that RefCell will never share references between threads. Okay, let's see at some code showing how to use cell. We have the immutable binding. There is no mute here. We create a structure that has some regular field and also a cell. And we are free to set the value of cell to 3. And if we try to print it, well, it works. Is it safe? Well, maybe not, and I will show you why. Because there is no borrow checking. So this example is a little bit convoluted, but I wanted hard to fit it on the one slide, so I will try to describe it. We have the imaginary database. For the sake of simplicity, here we only use it to keep single salary, 15K. Then we read the actual salary from the database. Then we calculate bonuses, passing the reference to the HR database. Here the salary is modified, but then probably not intentionally, we are setting again the previous value. And if you try to print the salary, you get the value without any bonus. You know, you feel safe and sound when writing Rust. Then you put one line too much and boom, shit hits the fan. If you use regular references, Rust will save you from this. Rust is able to save you from this bug. It will not compile your code. It will scream with these error messages that you cannot borrow as mutable because HR databases also borrowed as immutable kind of thing. And the RefCell that I'm going to describe on the next slide will also save you from this bug, but it will do it in runtime, not at the compile time. Oh yeah, and here is what I just said. Okay, here's the similar example with the RefCell. But by using RefCell, you need to explicitly gain access to the value stored inside. Like you need to ask RefCell if you can borrow this value mutably. Internally, RefCell will make sure that you cannot do it more than once at the same time, and will enforce any other borrow checker rules on runtime. So this code will compile and will also modify the value. Now we have a code that compiles well. It doesn't use any smart pointers. It's just a regular reference. We have the immutable reference, and in case, or maybe like that. This code compiles even though there is a possibility that there will be both mutable and immutable reference to the data at the same time. You know, I introduced this additional getUserInput method to emphasize that not everything might be known at compile time. So this code compiles because actually we don't use this reference after we created the mutable one. So Rust can be sure that it's not going to do any harm to have these both references at the same time. But if you decide that you're going to use this first reference after you created the second one, this code will not compile, even though that this body of the if might be never executed. So this is the situation when developer is trying to compile the code and says, okay, but I know that this will never execute. Why you are not allowing to compile? Here is the exact error message we're going to get. But we see that we have an immutable borrow, then we create mutable one, and then we try to use the immutable later. How to fix that? Well, unsafe. Yeah, we have this unsafe feature in Rust. Let's try to do it like that, but unfortunately it's not going to work. Unsafe doesn't mean that borrow checks are not enforced. So even if you claim your code might be unsafe, Rust will still enforce the borrow checking rules, and it will even happily let you know that this unsafe block is completely not necessary here. So we got another hammer in our toolbox. We can use the RefCell. So let's see what happens here. We put the data into the RefCell. We create one, let's say, reference. We borrow it once in the non-mutable way. Then inside the same if, we are trying to borrow it mutably, modify it, and print here, and also print at the end. And yes, it's fixed. It compiles, so you can ship it. What could go wrong? Yeah, it's gonna work correctly as long as the body of the if is not executed. In other case, you're gonna be slapped in the face, but only during the runtime. That RefCell will make sure that you're not gonna get this borrow mut, this mutable reference, if you are not allowed to. There are, of course, ways to prevent panic, like try borrow and this family of functions, so that you might prevent yourself from being caught with the proverbial pants down. RefCell allows you to disable compile time borrow checker. Rust will trust that you know what you're doing, but to trust doesn't mean not to control. As soon as you try to break the rules, you're slapped into the face. Okay, now let's see what we can do. We have the RC, which is the shared ownership, and we have the RefCell, which gives us mutability. So if you think about it, you can achieve the shared mutable state by using these two tools together. From the borrow checker point of view, this code is correct. Like we never create mutable reference. We only have the regular one, but we have the reference to something that can create the mutability for us. So let's go through it. We put the 23 in the RefCell that we put in RC. We are cloning the RefCell. Then inside this if, we are again cloning this RefCell, and we ask our RefCell to borrow this value mutably, and we modify it. So it works well, but the guy who relies on the data that he can receive through this reference might be a little bit surprised when he sees that this data were changed. Okay, so let me emphasize once again that this is appropriate in the single-threaded environment only. For multi-threaded one, you should use stuff like arc, rwlog, or mutex. Okay, and time for short summary. So prefer inherited mutability instead of the interior one, which means that you should try to create cell-less code. There's a checklist before using interior mutability. So my advice is not to simply follow the compiler suggestions. It often tells you that, consider borrowing, consider adding mut, and stuff like that. You will quickly go to the situation when this suggestions doesn't work and you still have compilation errors, but in different places. You end up with code that compiles, but it's not optimal. For example, you create copies where they are not needed. And I think the most important issue is that you don't learn. And my way to learn was not to look at what Rust is trying to suggest me, but try to understand what is going on by just looking at the code. And once you understand why Rust is complaining at your code and doesn't want to compile it, you can usually make a few steps back and come up with a better, more clear solution to the algorithm you're trying to implement. And this new solution will most probably be much safer and will be accepted by the borrow checker. Yeah, okay. And that's all I have for you today. So thank you very much for listening, and I see there are still few guys with us, so I'm glad you make it to the end. Thank you.